All right, let's dive right in. Today, we're talking about the absolute bedrock of all modern software, data structures and algorithms. You can think of them as the essential blueprint that every single programmer uses to build our digital world, from the simplest app on your phone to the most complex AI. So let's get into it.
So why are we starting here? Well, because honestly, understanding this stuff can have a massive impact on your career. I mean, this quote from Geeks for Geeks really says it all, doesn't it? Mastering DSA isn't just some academic exercise. No way. It's the key that unlocks the doors at the biggest tech companies in the world.
So, for our first section, let's break down exactly why data structures and algorithms matter so much. And trust me, it goes way beyond just passing an interview. This is about the fundamental quality, the speed, and the efficiency of the software you write.
At its heart, DSA is really about two things: how we organize our information and the game plan we create to actually work with it. It's about storing data in a way that's smart and super easy to access. It's how we solve incredibly complex problems, like how your GPS finds the fastest route or how a search engine sifts through billions of pages in a split second. This is the difference between clunky, slow code and elegant, high-performance software.
And that brings us right to the first half of this equation, data structures. We get why they're important, but what exactly are they?
This definition from IBM is just perfect in its simplicity. A data structure basically takes all this raw, abstract info, just a bunch of numbers and letters, and it gives it a shape, a format that a computer can actually understand and use.
And here's a perfect example to make that concrete. Instead of just 5 random separate numbers, we now have a single, organized structure called daily_sales. This is a simple list, or what programmers call an array, and it's one of the most fundamental data structures out there. See? We've given our data a home.
And once that data has a structure, that's when the magic happens. Now we can perform really powerful operations on it. We can sort those sales figures from lowest to highest, we can search for one specific day's total, or we can delete an entry we don't need. The structure is what enables the action.
Now, not all structures are simple lists like that one. They generally fall into 2 main architectural styles. So let's take a look at the difference between what we call linear and nonlinear structures.
Okay, on the left, you've got linear structures. They're exactly what they sound like. Data arranged in a line, one after another, kind of like a train. It's super simple to go from the start to the finish. But on the right, nonlinear structures are way more complex. Think of a family tree or a map of all your friends on social media. The data is all connected in a hierarchy or a web. You can't just visit everything in one single pass.
Okay, you ready? Let's go on a quick tour of the most common data structures you'll run into. Think of these as the essential building materials you'll be using to construct your programs.
First up, the stack. The key phrase here is last in, first out. Just imagine a stack of plates. You always take the one off the top first, right? Well, that's the exact logic behind the undo button in pretty much any application you use.
Next is the queue, which is, you guessed it, the exact opposite. It's first in, first out. It works just like a real-life waiting line, so it's perfect for managing things that need to happen in order, like a music playlist or a call center's waiting list.
Then we've got the linked list. This one's pretty clever. Instead of storing items right next to each other in memory, it connects them with pointers. This makes it incredibly flexible for things that change all the time, like your web browser's history when you're clicking the back button.
All right, let's jump over to a nonlinear one, the tree. It is absolutely perfect for representing hierarchies. You have a single root at the very top that branches out into children. Your computer's file system with all its folders and subfolders, that's a classic tree structure.
And next up is the graph. This is basically a collection of nodes, or vertices, that are connected by edges. This makes it the ultimate tool for modeling complex networks. Think about it. A social network where people are the nodes and their friendships are the edges connecting them. That's a graph. And finally, we have the hash table. Its superpower is just pure speed. It uses a special function to instantly map a key, like a person's name, directly to its value, like their phone number. This is exactly why searching through your phone's contacts is practically instantaneous.
Okay, so we have our structures, we have our building materials. Now we need the instructions, right? The recipes that tell us what to do with them. And that, my friends, is where algorithms come in.
At the end of the day, an algorithm is simply a step-by-step procedure for solving a problem. So if a data structure is the bookshelf, the algorithm is the set of instructions for how to find a specific book on that shelf, or maybe how to arrange all the books alphabetically.
But here's the thing, there's almost always more than one way to solve a problem. You could have two totally different algorithms that both sort a list of numbers correctly. So how do we know which one is better? How can we actually measure its efficiency?
While we do it with something called asymptotic notation. It's basically a mathematical way to describe how an algorithm performs as the amount of data it's working with gets bigger and bigger. You've got big O, which describes the absolute worst case scenario, then there's omega for the best case, and theta for the average case.
Now, in the real world, in the tech industry, developers almost always focus on big O. And why is that? Well, because you have to know how your code is going to perform under maximum stress. You have to plan for the worst possible case to build strong, robust systems. But here's a really key insight. Efficiency isn't just about speed. Sometimes the fastest algorithm, the one with the best big O for time, might use a ton of memory. It's this constant, crucial trade-off between time and space.
So we've covered the what and the why. But how do you actually go about learning all this stuff? Let's wrap things up with a clear, actionable roadmap you can follow.
This 5-step plan from Geeks for Geeks is a fantastic guide. Step 1. Pick a language. Any popular one will do, and just get comfortable with it. Step 2. Learn all those data structures we just toured. Step 3. Learn the algorithms that actually use them. 4. Really understand complexity, like those big O trade-offs we just talked about. And then the most important step of all, Step 5. Practice, practice, and then practice some more.
So you see, data structures and algorithms, they aren't just about code. They are the fundamental blueprint for computational thinking, for problem solving itself. It's a way of looking at the world that helps you build better, smarter, and more efficient software. So the only question left is, now that you have the blueprint, what are you going to build first?